So thank you for the introduction. Today I'll be talking about our approach to enabling bandwidth efficiency and low latency in data center networks. And in the context of data centers, there are a number of types of networks that are relevant, from rack scale to wide area. And in this talk, I'm going to be focusing on networks that connect thousands of racks of servers within a single data center or a data center campus environment. And it's important to innovate in this space because these networks are getting more and more difficult to build over time. So this graph is showing the required bandwidth for Google's networks and how that's changing over time. And the issue here is that the components that are used to build these networks, the packet switch chips, are scaling in bandwidth at a much slower rate. So this is a log scale here on the y-axis. And the growing gap in bandwidth between the components and the overall network means that networks need to use more hardware and are becoming more expensive and power hungry. And as if addressing that wasn't difficult enough, just keeping the components on their current scaling trend is becoming more and more challenging as we look forward for a number of reasons. So in response to these challenges, operators and researchers are sort of rethinking how best to optimize these networks for cost and power, and really aiming to minimize the amount of hardware that's necessary, all without sacrificing workload performance. So along this line of research, recently the community has proposed this idea of expander graph networks for data centers. And the basic idea with expanders is that you remove all of the layers of switches and cables that you'd normally find in a fat tree network, and instead just connect racks of servers directly to one another. And the cabling here can either be random or follow pseudo-random deterministic construction methods. And expanders are interesting because they can save significant hardware cost and power. You can build them to be comparable to heavily oversubscribed fat tree networks. However, they've been shown to offer higher throughputs than oversubscribed fat tree networks, specifically when the overall traffic load on the network is relatively low. And they do this by routing traffic along multi-hop paths through this network. So racks that don't have a direct connection between them, say these two racks shown in orange here, traffic is routed between those racks along these multi-hop paths. Now, the issue with using multi-hop paths, though, is that you pay what I'm going to refer to here as a bandwidth tax. So the bandwidth tax is a reduction in the throughput when the load is high, and that reduction is proportional to the average path length in the network. And this is just because every packet that goes through an intermediate top-of-rack switch consumes bandwidth resources at that switch. So to see the effect of the bandwidth tax, let's consider a second flow in this network between the racks shown here in blue. So traffic that's part of the second flow takes some of the same hops that traffic in the first flow took. So this leads to contention because the two flows now have to share the bandwidth resources along this link. And if we consider all the different paths that traffic may take, we see that the throughput is reduced here by a factor of 2, and that's because traffic is taking 2 hops in this network. So while expanders have a lot of great properties when traffic load is low, at high load, they can't deliver high throughput in general, especially when they're built to save significant amounts of hardware cost and power. So you may be wondering at this point if it's even possible to support high traffic loads with these networks that try to save significant amounts of cost and power. And so it turns out that reconfigurable networks can get us this property. So in reconfigurable networks, we can reconfigure some of the links that are not so useful for the current traffic demand and reconfigure them into direct links between communicating racks. And so these direct links have the minimum bandwidth tax here, 1, because they don't consume any bandwidth resources elsewhere in the network. The traffic is just sent directly from one rack to another. So reconfigurable networks get us this property that we can have high throughput even when traffic load is very high. However, there are a number of challenges to implementing these reconfigurable networks. So one has always been how to decide which links to reconfigure and when to do that reconfiguration. This typically will lead to a complex control plane to make all these decisions. So we can sidestep this complexity by adopting designs such as RotorNet, which we proposed a few years ago at SIGCOMM. And if you're not familiar, the basic idea behind RotorNet is to step through a deterministic and predefined schedule of connections rather than trying to compute that in real time during network operation. But even if we can avoid the control complexity, the issue still is that today's circuit switching technologies, the type that scale to the sizes to be practical in large-scale data center deployments, just reconfigure too slowly. And so this introduces latency into the network and isn't really compatible with some of the low latency workloads we find in data centers today. So now we kind of have this dichotomy where reconfigurable networks can get us high throughput, but they have high latency. And then static expander networks have the inverse properties. So if we consider a workload and partition it into short flows that are latency bound and long flows that are throughput bound, we see that each of these types of networks can really only support a portion of the traffic in this workload. But stated a different way, if we could build a network that had some of the properties of each of these two network types, then we could support both types of traffic effectively. And so our contribution here is to enable a network that does this with a design we call Opera. So now I'll kind of go through some of the high-level design aspects of Opera. So the first design property we'd like to have is for Opera to provide low bandwidth tax connectivity. And to do this, we use reconfiguration. So we connect racks of servers with reconfigurable circuit switches. And the circuit switches can establish these direct connections between racks. And I'll define a term here that I'll use for the remainder of the talk called a matching. And a matching just means each rack, each source rack is connected to a single destination rack. So this connectivity shown here in blue is an example of a matching. Now this matching only connects some of the racks together. So if we draw from the RotorNet design architecture, we can step through a sequence of matchings that connect different pairs of racks together. And it turns out that we only need to step through n matchings to connect n racks all directly to one another. So this is kind of the substrate to enable this low bandwidth tax connectivity. So next I'll talk about how we enable low latency connectivity. So in a real network, we don't just have a single circuit switch connecting racks, we have multiple circuit switches. And so this enables us to step through these matchings in parallel rather than in series. And so at any given time, we have multiple matchings that are active. And so one of the key insights in Opera is that if we design these matchings appropriately, we can actually ensure that they form an expander graph. So another way to think about stepping through these matchings, in addition to providing this direct connectivity over time, at any given time, we're implementing an expander graph. So to see what this gets us, I'll step through a small example. Let's say that the racks colored in red want to exchange traffic, and let's say that the circuit switches are currently implementing these matchings 1 through 3. And let's also say that there's no direct connections between the two red racks in any of these matchings. If we treat these matchings, their union as an expander though, we can guarantee that there are multi-hop paths between these racks. And so what this means is that the short latency bound flows can be sent immediately without waiting for the network to do any reconfiguration over these multi-hop paths, albeit for a higher bandwidth tax because they're taking multiple hops. Conversely, the long throughput bound flows that can afford to pay a short latency penalty can wait for these direct paths to come up in the network, and they can be sent then for a lower bandwidth tax. So a key property of Opera then is that unlike a static expander network, which pays a bandwidth tax for all traffic, Opera is only paying a bandwidth tax for the fraction of traffic that comprises the short flows. And so if we're running a workload that has both short and long flows, this can lead to a lower average bandwidth tax, or stated differently, higher throughput in Opera. So now I'll briefly talk about how we actually choose these matchings to enable these properties. So the first property we want is good expansion. So from graph theory, we know that the union of 3 or more matchings is an expander, as long as those matchings are randomly structured. So random structure is the first requirement on the matchings. The second piece is enabling this direct connectivity. So to do this, we start out with a fully connected graph. That's the fully populated matrix shown there, and decompose that into n randomly structured and disjoint matchings. So those are the colored sparse permutation matrices shown on the right. And the point I'd like to emphasize here is that this computation can be done offline before network operation. So there's no active circuit scheduling here. We just compute the structure of these matchings ahead of time and then load them into the circuit switches, which deterministically step through these matchings. So now we have this deterministic sequence of matchings that repeats over time, but there's one other piece that we have to consider here, which is that circuit switches take a non-zero amount of time to reconfigure. And during this reconfiguration time, they can't carry any traffic. And so for kind of state-of-the-art circuit switch technologies, that can be on the order of tens of microseconds. So if we were to reconfigure all circuit switches simultaneously, we'd have these periodic windows where the network couldn't admit any traffic. And that could really hurt the latency performance of short flows. So what we do instead is stagger the reconfiguration of the switches so that at any given time, most circuit switches are active and we can get the properties, the expansion properties that we want at all points in time. So now given these time constants of the switches and given modern link speeds, 10 to 100 gigabit per second, it takes Opera between 1 and 10 milliseconds to step through all of the matchings. And so we can think of this as the time it takes for a specific direct connection to come up in the network. So this is really driving what we're considering as the cutoff between kind of short and long flows in Opera. So I won't go into the details here. I'll refer you to the paper, but for 10 to 100 gigabit per second links, this cutoff lands at about 15 to 30 megabytes. So flows that are longer than this can afford to wait for these direct paths, but flows that are shorter than this would have their flow completion time inflated significantly if they waited for the direct paths. So those flows have to take the multi-hop paths. So if we look at data center network traffic, these published flow distributions, we see that most flows in these workloads would be classified as short flows. So most flows would have to pay this bandwidth tax in Opera. However, talking about the number of flows is not really the right metric here. If we replot that same data as a CDF on the number of bytes, what we see is that most bytes that are sent across the network are actually contained in a small number of very long flows. And so what that means is most bytes can actually avoid paying the bandwidth tax by waiting for these direct paths. So this is sort of promising at a high level for these workloads. And next I'll talk about some packet simulations we did to quantify performance even more. So just to set the stage, these are packet level simulations, and so we were restricted to simulating relatively small networks. So the networks I'll be talking about here have about 100 racks. So the first workload we considered was an all-to-all shuffle. So every server sends data to every other server. And this is a favorable workload for Opera because it places a very high load, traffic load on the network. And so Opera is able to take advantage of these direct paths and send all traffic over to the direct paths in this case. So it avoids paying a bandwidth tax and achieves very high throughput and fast job completion time. So we ran the same traffic pattern over static networks, both an expander graph and a 3-to-1 oversubscribed VAT tree, which were equal in cost to Opera. And those networks take longer to complete the shuffle because they're paying this bandwidth tax for this traffic. So next, we considered a more challenging workload for Opera. So in addition to the shuffle, we ran a web search workload. And in the web search workload, all the flows are very short, and so they all have to pay the bandwidth tax in Opera. So we started out with a very light web search traffic load, 1% of the bisection bandwidth. And at this point, Opera is performing quite well in terms of throughput and offers comparable 99th percentile flow completion times for the short flows. We then increased the load of the web search traffic to 5% and then 10%. And so we see that Opera's throughput is dropping as we increase the load of this low latency traffic. And that's just because more traffic is having to pay a bandwidth tax here in Opera. But even at 10% of bisection bandwidth dedicated to this web search workload, Opera provides twice the throughput and has comparable 99th percentile flow completion times to the other networks. So finally, we looked at a third workload, which was a data mining workload that included flows between 100 bytes all the way up to a gigabyte. And in that case, we saw that Opera could admit about 60% higher load than the other networks. So in addition to packet simulations, we looked at a few practical considerations for deploying Opera, one being fault tolerance. So we found that Opera can maintain full connectivity between all working components, even if it loses a moderate amount of links, top-of-rack switches, or circuit switches. And further, because Opera is stepping through this kind of all-to-all direct connectivity, we can take advantage of that to detect and disseminate failures on the time scale it takes to step through those matchings, which is about 1 to 10 milliseconds. We also looked at implementing Opera's forwarding and routing protocols on commodity programmable packet switch hardware with P4. And this showed that Opera can scale to thousands of racks, tens of thousands of servers when constrained to the table sizes in commodity switches. So with that, I'll just summarize by saying that Opera provides higher throughput than cost-comparable static networks for a variety of workloads that include large flows or messages without compromising the latency performance of short flows. And it does this without introducing the complexities that are typically associated with reconfigurable networks. Thank you. So happy to take questions.
We have time for a few questions. Oh, you feel free to walk up to the microphone. Go ahead.
So what is the port count of an Opera switch?
Yeah, so I didn't really talk too much about hardware here. The switches that we'd be most interested in using, so you could use any circuit switch really, and it's just going to affect the time it takes to step through the matchings depending on its reconfiguration delay. So the circuit switches we'd be interested in using reconfigure in about 10 microseconds and have a port count of the order of a few thousand ports. So it actually lines up pretty well with how many racks you can support with the routing state.
Thanks.
Okay. Yeah, so I have, it's not just questions, but just want to know about this a little bit. So when you say the expander, when you construct it, is it non-blocking or it is blocking?
Well, so I guess it's blocking in the sense that traffic has to make multiple hops through the network.
And then the follow-up question is, if it is non-blocking, then could you say something about this and the non-blocking expander?
Well, so I think Non-blocking is typically used in the context of fat tree or folded clo networks. I would say that I'm not familiar with that term being applied to expanders, so I don't really know how to speak to that, but I would just say that in a folded clo, traffic is taking multiple hops through the hierarchy, and in the expander, traffic is making multiple hops between racks. And so if you're talking about latency, the latencies can be comparable. If you're talking about throughput, the folded clo is paying for these multiple levels of hardware versus the expander is not. But then the expander has lower throughput at higher load. So that's kind of the trade-off there. Maybe that answers your question.
Thank you so much.
We have time for just a very quick question. This will be like quick answer and a quick question.
Okay. I just want to make sure that I get the whole picture right as well. So it's more like affirmation. So basically, you're treating all the top of rack switches where they are connected together like one big switch, and you're trying to see the flows and you try to do some deterministic, let's say, algorithm. But in that case, I just want to make sure that when you take in this data center, you're not assuming that there is a distribution layer on top of the top of rack switch, which basically is going to go to the, let's say, from the source destination to the distribution layer, and then directly to the destination. This is your assumption?
I'm not sure I caught all that, but in our design, basically, there's the top of rack switch, and then there are these transparent circuit switches that connect the top of rack switches. So you can think of those as basically cables connecting the top of rack switches, and we can just change the configuration of those cables.
One big switch. So you're not assuming the distribution layer on top of
No,
the other
no,
routing.
nothing about that.
That's
Yeah. Thank you.
Okay, let's thank Max.